we are going to do some U substitution. I've got a new microphone today, so hopefully my voice sounds beautifully clear. We're just going to be working a series of problems here, again, using U substitution. These are all indefinite integrals. These came from Calculus by Howard Anton, 2nd edition. All right, U substitution. Once again, these are all indefinite integrals. All right, so the point behind U substitution is if you can take, we can easily take the integral of simple things like the integral of x or x squared, or the integral of cosine x or sine x. But when it's something more than x, okay, then that can start to become a problem for us. Okay? Well, we can fix that by using, as I said, U substitution. So in this case, the goal is to choose something to represent U that's going to be helpful to you. So here we're going to make U equal to pi x minus 3. Now if U is equal to pi x minus 3, then the derivative of U, or du, is simply going to be pi, and then don't forget the chain rule, dx. So the goal when using U substitution is that I choose a U, and then the result of taking that derivative of U will then let me represent everything I have in my original integral. In other words, I've got a dx here. So if I'm going to use U, then my du needs to account for that dx, and it does. There's a dx right there. But my du in this case also has a pi. I don't have a pi here, but that's okay. Because pi is a constant, I can counteract that by just putting a 1 over pi outside my integral. So right now, if this is U, my integral now looks like this: 5 cosine U du. Okay, I plugged pi x minus 3, I substituted that for U, and there's my du. It contains dx, so we're okay there. That dx is still in there. And it also has a pi, but I've allowed for that by putting a 1 over pi out here. So before I actually solve this, I'm going to go and bring the 5 out front as well. So this becomes 5 over pi, the integral of cosine U du. Alrighty. Well, you know how to take the integral of that. This is going to be 5 pi. The derivative of cosine, the integral of cosine is sine. So this is going to be sine of U. So 5 over pi sine U. I'm now going to substitute my U back in. So this becomes 5 pi sine of pi x minus 3. Now remember though, this is an indefinite integral, so in the last I'm going to tack on a plus c, because that could be any constant. Yes. So there you go. The integral of 5 cosine quantity pi x minus 3 is equal to 5 over pi sine quantity pi x minus 3. Now, I trust this probably looks a little more complicated than you might have just been able to do without U substitution. Perhaps, you know, when you get good enough at it, you can look at that and figure that out. But U substitution just makes things really easy, particularly when you're just starting out learning how to integrate. All right? So let's have a look-see at this one here. Integral of 1 over root 3s plus 1. Well, it's pretty obvious what we're going to want to make our U here. Our U will just be whatever's in the square root. Don't include the square root. We'll make U equal to 3s plus 1. Because then du will be equal to 3 ds. In other words, the derivative of 3s plus 1 is 3, and then chain rule, ds. So once again, if I'm going to use this as my u substitution, I have to have everything accounted for in my du that's in my original. And I have a ds, there's a ds, that's good. Now I don't have a 3, but again, because 3 is a constant, I can put that out front. So this becomes 1/3, that accounts for the 3. The integral of 1 over root u d u. And there you are. Now to take the integral of this, I'm going to rewrite this as u to the minus 1/2 du. All right, and we can take the integral of that, right? You've done that by now. So this is going to be 1/3. The integral of that, well, to add to that, I'm going to have to get it up to 1/2. That'll give me the minus 1/2 when I take the derivative. Blah, 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 blah. Okay, anyway, I need to counteract that 1/2 with a 2. So the derivative of u to the minus 1/2 is 2u to the 1/2. And you can test that real quick. Is that true? Sure. Because if I take the derivative of 2u to the 1/2, I bring my 1/2 down, 2 times 1/2 cancels out, that's gone then, and I just have u to the 1/2 minus 1, which is u to the minus 1/2. There you go. So once again, I'll simplify things to bring my 2 out, so I have 2/3, and substitute my u back in there, so that's going to be 3s plus 1 to the 1/2. You could write the square root of 3s plus 1. And again, this is an indefinite integral, so plus c. So there is the derivative of that. There, derivative of that. Excellent. Excellent. Okay, all right, so here we have a nice tricky one, right? No numbers this time, but a and b, of course, represent numbers. My variables are x here, and n's just some number. We don't know what it is. So we can adapt a general form for solving integrals of this nature, okay? And we'll do it using u substitution. So again, I think it's pretty clear what my u is going to be. I will make u equal to a plus b x. Good. That means my du will be the derivative of that. Well, the derivative of a plus bx, the a's gone. This is just going to be b dx. So if I look back at my original equation, my du has to include everything that's not part of my u, and so there's the dx. I got that right there and there. I don't have a b, but b is a constant, so I can account for that by putting a 1 over b outside. So now this is going to become the nth root of u du. And again, to make that perhaps a little more straightforward, I'll write this as a fractional exponent. The nth root of u is equal to u to the 1 over n du. All right, so what's the integral of that? Well, it's 1 over b. And let's see, u to the 1 over n. I have to add 1 to that. That's n over n. So n over n plus 1 over n is n plus 1 over n. But remember, I don't have n plus 1 over n in my integral, so I need to allow for that or counteract that, however you want to phrase that. So n plus 1 over n becomes n over n plus 1, and then u to the n plus 1 over n. So again, we can double check ourselves. If I take the derivative of this, I should wind up with that. Do I? Well, I bring my exponent down as a coefficient, n plus 1 over n. That cancels with this. That's good. That's gone then. And I have u to the n plus 1 over n minus 1, which is minus n over n. N plus 1 over n minus n over n is 1 over n. So yeah, we're good. We're good to go here. So my final answer will be written as, I'm going to bring this out, so that'll be n over b times n plus 1. My u, you will recall, is a plus bx. So a plus bx to the n plus 1 over n. And again, lastly, plus c. Don't forget that plus c. Okay, excellent. Now, where u substitution really comes in handy is when we've got more complicated trigonometric integrals we're going to do. Slide that up there. There we go. So we're going to solve this one here now. All right, so we have the sine of x to the 6th, sine to the 6th of x, cosine times cosine x dx. All right, so in this case, I could make u equal to cosine x, but if I did, then I would have a sine x dx in my du, which means I'd still have a sine to the 5th x. It would just make it messier. So in this case, we're going to make u equal to the sine of x. That's going to be much more friendly. That means du is equal to the derivative of this is just cosine x dx. Okay, so once again, my du has to include everything that's not part of my u. So my u is going to be the sine x. My du is cosine x dx. Well, there's cosine x dx right there, isn't there? Yes, that'll make a lovely substitution. So this, after I plug in my u, becomes this. U to the 6th du. Because the sine of x is the u, and the du is the cosine x dx. There we go. So we can easily take the integral of that. That is 1 over 7 u to the 7th. And when I plug that in there, that's 1 over 7 sine to the 7th x. And again, finally, remember your plus c. Very nice. Well done. Okay, let's do this one right there. X squared, x cubed plus 1. And so now you see you're starting to look ahead, right? You know that your du's got to include the dx and anything else. And sure, if we let u equal to x cubed plus 1, the derivative of that will be x squared dx. Okay, so that'll account for that. So let's do that. Let's make u equal to x cubed plus 1. That means du will be equal to 3x squared dx. Well, there's my x squared dx. That's all accounted for. I can substitute that in there very nicely. But I don't have a 3, do I? But we can fix that by putting a 1 over 3 outside the front. So this becomes, there's my x squared dx. This becomes 1 over the square root of u du. The x cubed plus 1 is my u. That's under the radical. And the du includes the x squared dx, which is right there. And I account for the 3 by putting a 1/3 out front there. So we just need to solve this. And we actually already did that up above, but let's do it again. 1/3. Just to make this easier, I'm going to write this as u to the minus 1/2 du. Okie dokie. Well, to take the antiderivative of that, or to integrate it, I have to add 1 to that, so that becomes 1/2. So when I take the integral of that, it's going to be 1/3. The integral of that will be 2, because I got to counteract the 1/2, 2 u to the positive 1/2. All right, there you go. And I will simplify that out here by bringing the 2 out front. So this becomes 2/3. And I've got then x cubed plus 1, so putting u back in, 2 the 1/2, and finally plus c. There you go. Okay. All right. Let's look at this one here. Here we have tangent x, the square root of tangent x times secant x dx. How would we integrate that? Well, prior to your u-substitution days, that would have looked nigh impossible. But now, it's the simplest thing, really. Because if we make u equal to the tangent of x, you will recall that the derivative of tangent is secant squared x. And the derivative of tangent x is secant squared x dx. So lo and behold, I need a secant squared x dx in order to use a substitution. I have a secant squared x dx. So this is just going to become the square root of u du. Look at that. That is cinchy. All right, well, if you like, we can write that as u to the 1/2 du, and you know how to integrate that, right? We add 1, that'll get us up to 3/2, so I've got to counteract that, so this becomes 2/3 u to the 3/2. And again, you can double check that. If I take the derivative of this, I should get u to the 1/2. I do. 3/2 times 2/3 is 1. U to the 3/2 minus 1, that's 3/2 minus 2/2, which is 1/2. Alrighty, so let me substitute my u back in, so this becomes 2/3 tangent 3/2 x, and then finally plus c. Well, there you go. If you don't like that fractional exponent sitting up there, we can fix that. We can write this as 2/3. That would be the square root of tan cubed x plus c. There you go. Same difference. All right, let's see what we got here. Last couple here. Okay, there's that one. Sine of sine of theta, cosine theta, d theta. So once again, without u substitution, we're looking at that, we're thinking, what? But with u substitution, it becomes simplicity in itself. So in this case, we will make u equal to sine of theta. And if you're wondering, well, how does he know what to make u? Well, I've had practice, and it'll get easy for you too once you practice a few of these. It'll become pretty clear what you need to make u. So in this case, if u is sine theta, then the derivative of sine theta is cosine theta d theta. Well, I have a cosine theta d theta right there, don't I? That'll make a lovely du. So now this is going to become the sine of u du. Everything's accounted for, right? There's my u right there, sine theta, and there's my du, cosine theta, d theta. All right then. Well, we know how to take the integral of sine of u, do we not? Yes, we do. It is minus cosine u. Because the derivative of cosine is minus sine, but I have a positive sign, so that's what that minus sign is there for. And so I'm going to substitute my u back in here, so this should be minus cosine of sine of theta, and it's an indefinite integral, so plus c. See, so that rather vexing looking problem turns out to be really quite simple. There you go. And again, if you doubt yourself, you can take the derivative of that. You know how to take derivatives using the chain rule and all that. You should be good. All right. Okay, this one looks problematic. It's not going to be, but it's another one of these with the A's and the B's and all that stuff. Okay, so we have sine to the n of a plus bx times the cosine of a plus bx dx. So we've seen this sort of problem before. We know we want our u to be sine because that will give us the cosine dx that we're looking for. So we're going to make our u equal to the sine of a plus bx, which means the derivative of u will be cosine a plus bx. Now remember, we have to use the chain rule. So now to find du, I still have to take the derivative of what's in the parentheses. So it's going to be times b. All right, so when I look to do my substitution, I'll be substituting u in for that. We'll have u to the n. And then to put du in there, I have to have a cosine a plus bx, which I have. Oh, I forgot. Sorry. Forgot my dx. There we go. And I have my dx, good. What I don't have is a b, but b is just a constant. So I can fix that by putting a 1 over b out front. So this just becomes, if u is sine a plus bx, this becomes u to the n. There you go. Look at that. We took that ugly looking thing and turned it into something really quite simple and straightforward. So let's integrate that. Well, that's going to be 1 over b, of course. The integral of that right there, well, I need to add 1 to that, right? So n will be n plus 1. So in my integral will be 1 over n plus 1 u to the n plus 1. Yeah. You've done problems like that before. Even if you haven't used n's and u's, you've done them with, x cubed and all that stuff. You know how to do that. All right, so when I plug everything back in here, I'm going to bring this outside. So I have 1 over b times a quantity n plus 1. And my u is going to be the sine, and this will be to the n plus 1 of a plus b x, and again, finally, plus c. So there you go. U-substitution. So, and as I say, it'll get easier for you as you get a little practice. All right. I just knocked over the microphone. We'll see if that shows up on the video.